Hey everyone, thanks for coming to my talk. So my name's Dora. You can find me in all the usual places online. I'm based in London and I have a pet fox called Franklin. I used to work at the Financial Times where I was a tech lead and a member of the Cybersecurity Guild. And these days I work as a developer relations engineer for Fastly on the compute team, which just means that I spend a lot of time thinking about advanced serverless technologies. Zen, in the context of the title of my talk, is all about being relaxed and unbothered about stuff that is beyond your control. And this is what I like in my architecture. It needs to be resilient enough to be conducive to Zen. Now, when I say edge, I mean it in the context of edge computing, again, in the context of large-scale distributed coordination-free systems. And I mean that as bringing computation and data as close as possible to where it's needed, whilst retaining control of the environment. So if you work with the Internet of Things, that point, the edge, is your thing that's on the internet. But for most of us, that point, the last point where things are still in your control and not in the Wild West where people use, whatever device to connect and interact with your service, that point is the network's edge. Authentication, in the context of secure login flows, is the process of verifying the identity of a person or a device. And it is not very Zen at all. So whether you're a DevOps professional or an engineer, there is a lot of stuff that goes into building a truly secure system and a lot of stuff that you need to know about when you're building authentication. And it's just super easy to get wrong, which is a little bit surprising if you consider what an essential thing it is and how it's everywhere. But we've been getting it wrong for a very long time. So OWASP, or the Open Worldwide Application Security Project, has been doing this awareness piece for like the past decade. They break it out every couple of years or so, and it's all like categorizing the top risks for web application development. And broken authentication has been at the top of that list since its inception. Except there is hope, that might actually change. In 2022, in summer at WWDC, Apple introduced this very promising technology called passkeys, and then the world went wild. So passkeys are promising that you'll be able to log in securely on the web without using a password. And everybody, I mean, people outside of the usual technology sphere started reporting, okay, password is dead, we're all going to have such a brilliant time. And you know what, The Guardian did not write about OAuth 2 when that came out. So I'm pretty sure this is going to be great. Hands up if you've ever experienced passkeys on the web. Not a lot of people. Okay, so this is what it looks like to log in with your Face ID on an iPhone to a website. And if you've never used passkeys before, I'm going to encourage you to scan that QR code or go to that devchat.edgecompute.app and experience them right now. So this is like a real-time little web application that I built just for DevOps-Exchange London, and you can all chat to each other and say hi and make friends, or drop me any questions that you may have about passkeys for later. And you register and you log in using a passkey. Passkey is the plain English word for something called FIDO multi-device credential. FIDO stands for Fast Identity Online, and that's like an open industry standard developed by a bunch of companies in an alliance, and they all want to make authentication better and more user-friendly and more secure. A credential is something that you use to verify your identity. Now, username and password, that's something everybody knows about. That is called a knowledge-based credential, because a password is something that you know. And usually this password is shared, it's a shared secret, and it's stored by the server, and the responsibility for securing it lies with the service provider, or he who builds the thing. Now, FIDO are trying to push authentication towards possession-based credentials, which are stuff like biometrics or hardware tokens like YubiKeys, stuff like that, stuff that you possess, stuff that is on a device in your possession. And crucially, the responsibility for securing those doesn't lie with the service provider. It lies with the platform vendor, with the device vendor. And yeah, to the same extent that responsibility for password lies with you, responsibility for the device that you're in also lies with you for securing them. And FIDO also dictates that passkeys are necessarily multi-device. So you should be able to use the same biometrics or YubiKey login to log into a website on any devices that you own that are synced, usually via your Apple ID or your Microsoft or Google account. And you might find some more literature that refers to passkeys as discoverable WebAuthn credentials. So the idea that they're discoverable means that they support an auth flow where you don't need to enter a username or any other info, and it's just going to work. So in theory, because browser support for this bit is it's still in the works, but that's coming. And WebAuthn is just simply the web correspondent of the FIDO standards. And it makes passwordless authentication possible on the web through something called public key cryptography. Crash course. Public key cryptography is very hard to say quickly, and it uses something called a key pair, a pair of keys, in order to enable secure communication and data protection. There's two keys in a key pair, a private one, which is kept secret by one of the communicating parties, and a public key, which can be shared freely across the network. Now, the key pair can be used for a series of cryptographic operations like encryption and signing. Encryption is the thing that ensures data confidentiality. So you use a public key, your own public key, to encrypt something, and only the matching private key can be used to decrypt or decipher that message. Also, you can use it for signing. And signing is something that safeguards data authenticity and integrity. So when you sign something, you use your private key to create a digital signature. And then the matching public key can be used to verify that the signature is authentically yours, and also that the data hasn't changed or been tampered with since you signed it. Take Bob and Alice, for example. Say that Bob wants to send a secret message to Alice. Alice has a key pair. She keeps the private key safe, like a secret place, and is going to give Bob her public key. Bob's going to take a plain text message. He's going to use Alice's public key to encrypt it. And because Alice hasn't shared her private key with anybody, Bob can then trust that only she can read that message. Now, the public key, Alice's public key, is not a secret. So anyone who isn't Bob can use it to send secret messages to Alice. So if Bob wants to make sure that Alice can verify that a message comes from him, then he needs a key pair of his own. And he's going to use a private key to sign a message, and then he's going to give his public key to Alice. And Alice can use that public key to verify that the message she receives is indeed from Bob and is exactly as Bob has meant it. So that was the crash course. In summary, key pair, public key, private key. These are cryptographic inverses of each other. So what the public key encrypts, the private key decrypts. And when the private key signs, the public key verifies. And you only need to keep one of these a secret. And the zen of WebAuthn is the fact that you're not responsible for keeping that secret. I'm going to explain in a sec. Just want to dig a little bit more into WebAuthn. And because people who write standards are massive nerds, WebAuthn has something called ceremonies. There's two ceremonies in WebAuthn: registration and authentication. And these take part in the sort of choreographed dance between four parties: the user, or you, or whoever's trying to log in; the client, which is your front end, can be a web app, can be something like that; the server, or relying party, or RP, as I'll keep referring to it in the future, which is your backend, an API, whatever, your backend service; and an authenticator, which is a cryptographic capability that lives on the device that the user possesses, be that their phone or like a USB key or whatever. So let's dig into the registration ceremony of WebAuthn. This is just the screenshot from the app. You can try it out. You can use any passkey. I will explain why that's completely secure to do at a conference over public Wi-Fi in a bit. Here's what happens when you register. Typically, a user clicks a button like register using passkey, and the client on the front end is going to make a call to the RP, to the server, to the line party, to get something called registration options. And then the RP is going to answer that call by sending back some options. So it's going to send an object with like its own identifier and its own name and information about what types of keys are acceptable, what algorithms are okay for signing, and what authenticators are acceptable for this process. And it's also going to generate a random challenge that is going to store for later. Client gets all of this and calls the web authentication API with something called credentials create, and it passes the challenge that it got from the RP to the authenticator on the device. The authenticator is now possibly going to prompt the user to get verified, either using Face ID or your PIN, and you can even log into websites using your phone. It's a very well fleshed out spec. So you verify yourself. If you pass that verification, if you are indeed who you say you are, the authenticator is going to create a passkey, which is a key pair, and it's going to store it inside whatever secure cryptographic capability it has. It could be a TPM, it could be a secure enclave, it could be a USB stick, and it's going to use the private key part of this to sign the challenge it got from the RP. Then it's going to send the public key back, the signed challenge, and the credential ID for the passkey it just created back to the client. The client's going to take all of that and send it to the relying party. The relying party is going to look at the signed challenge and is going to verify it using the public key it just received against the challenge it stored earlier on. And if all that checks out, then yay, you've registered a passkey. And that passkey is uniquely associated with the website you've registered it for, both on your device and both on the server. And that's about it for registration. Now, authentication, the second web authent ceremony, is pretty analogous. The whole dance follows the same kind of winding route. And I'm going to explain it now. It starts with a click of a button, sign in with a passkey. The client is going to make a call to the RP to get the authentication options. The RP is going to respond with the options in the same way it responded during registration, and it's also going to generate another random challenge, which is going to store somewhere. The client is going to take all of this and is going to send it to the authenticator on the user's device, which then might prompt the user to get verified using a PIN, using their face, whatever. And if all of that checks out, then the authenticator can say, yay, you are who you say you are. I'm going to sign that challenge with the private key I have stored before, and I am going to give you back the signed challenge and a credential ID. Not the public key this time, because the authenticator expects the relying party to have stored it during the registration process. So the RP now gets a credential ID and a signed challenge. And it's going to use that credential ID to find the public key that it stored before during registration, and it's going to verify that the signed challenge it got back from the authenticator matches what it stored earlier in the authentication process. And if all that checks out, you're signed in. So yeah, I mean, where's the promise of passkey? So one of the big downfalls of password-based authentication is that passwords are a shared secret. And you're often forced to share it with parties that aren't in your control. You share it with a server, with the people who build the service that you're using. You share it over public Wi-Fi. And, you know, if a hacker manages to steal your password, they can pretty much fully impersonate you online. And hackers steal passwords all the time because, you know, the massive data breaches and phishing attacks, they're more common than you'd think. The whole thing about passkeys is that you're not actually sharing any secrets with anybody. So if someone breaches the relying party Or if they're listening in on the airport Wi-Fi, the most they can get is your public key, which is fine because that key is public. If someone is targeting you with a phishing attack and they manage to create a fake website that looks a lot like the website you've used to sign in, and they get you to register a passkey. That passkey won't be associated with a legitimate website. It will only work on the fake website, and it's like basically unhelpful. You can't use it to log into anything legitimate. So as far as service providers are concerned, ye who build the things, 5 minutes, thank you, I will do it. Passkeys are basically unbreachable and unphishable, and they're a fantastic thing. Okay, so how do we build this? If I want to build the perfect authentication, I want it to be fast and distributed. So I don't want it to cause any bottlenecks or to add any latency in my systems, and I don't want it to add friction in the user experience. Good authentication is also autonomous, so it's independent, isolated from the rest of the system to reduce the attack surface. It's also necessarily secure because it's got to be. And ideally, it's also like minimally annoying to integrate and maintain. And that's where edge compute comes in. So what is edge compute? Distributed systems are hard to do well at scale. We all probably know this. The architectures are hard to reason about. And it's like basically an art to plan and scale and think about infrastructure. And we as an industry came up with serverless as to try and go some of the way towards solving these challenges. And edge compute is the new kid on the block that tries to solve everything. So with edge compute, instead of relying on centralized cloud-based infrastructure, your computation and your data, you do that all at the network's edge, on the server that is closest to your user to minimize latency. And all of that happens kind of automatically. So you're freed from the challenges that come from, outsourcing your infrastructure like you do with serverless. And your teams gain huge operational benefit and efficiency. That app that I shared at the beginning of the chat app is an example of an edge compute application. And I built it, and I'm going to share the code because it's just, it turned into this neat little package that you can use to put passkey authentication in front of whatever, just in front of whatever you have. And I can do that because it's built on something called Fastly Compute. I work for Fastly. Probably you may never have heard of us. That's okay. Fastly is an edge cloud platform. So we do network services like CDN, we do security, observability, and also edge compute. And we have an absolutely enormous network. It's in 97 points of presence around the world with a super humongous global edge capacity in terms of connected capacity. About 80% of the world population is 20 milliseconds away from Fastly. And we serve something like 1.8 trillion requests every day. And our edge compute is simply compute capability running on every single one of those high-powered services around the world, instantly globally deployable without any thinking on your part. And every request that goes through Fastly Compute is serviced by its own isolated runtime environment. So there's no reuse instances like you'd have with Lambda. And this happens thanks to a small and self-contained assembly-like language called WebAssembly, or WASM. And you get really good security guarantees because it's basically like a very secure sandbox that you can run your code in. And the absolutely cool thing about WebAssembly applications is that they take no time at all to start up. So the execution startup time for WASM services running on Fastly Compute is something like less than 50 microseconds. Now, the last time I checked, the next container-based technology was over 100 milliseconds. So this orders of magnitudes faster. There's no cold starts or warm starts or warming up time to speak of with WASM here. So that's obviously a huge benefit over something like serverless. To write something for Fastly Compute, you can use any language that compiles to WebAssembly. Fastly support 3 officially, like Rust, JavaScript, and Go. And there's also growing community support. Our most well-supported other languages are Zig, Ruby, and Swift. And you can also deploy stuff to compute in all the ways you'd expect to with Terraform or GitHub, and there's a CLI and an API. And the platform itself is pretty feature-rich for just about any use case you can imagine. I've done ML on it. Authentication is my shtick, kind of. There's a lot of edge state storage for whatever your use purpose. There's stuff for config, there's stuff for secrets, there's key value stores, which are based on CRDTs, if anyone is a bit of a data nerd like that. So all of this, you don't have to worry about wrangling infrastructure or orchestration. And you also get real-time messaging for things like push, for WebSockets, and for PubSub. This is the architecture of the chat app I showed earlier. So the work of the relying party is done by a single fastly compute service. The user credentials also live on the edge in a KV store. The backend system is just a simple API that puts and retrieves messages from SQLite. And the real-time capabilities are also handled by the same service that does the whole relying party work, the cryptographic work that makes passwordless authentication possible. And I haven't had to think about scaling anything in this process, and it's been pretty zen. So if you want to learn more about this, if you want to look at the code, the URL on the left and the QR code on the left, zen-ed.auth.glitch.me. You get a bunch of resources there. I've put links to the standards. I've put links to the repositories. The code is written in JavaScript, so hopefully that's pretty accessible. But if that's not your thing, there is also an older live stream of me doing it in Rust, which I am personally probably more comfortable with. There's also, if you just like authentication but not necessarily passwordless, there's also implementations of auth, so just go and check that resource out. And if you have any questions, I don't have time, but I promise I will look at the chat. Thank you so much for having me.